So hello everyone. It's 9 o'clock, so it's time to start our seminar. I would like to welcome you here on this seminar, which is held in the frame of project R2P2. Today's topic is focused to mechanical metamaterials and then 3D printing technologies of used in robotic hands manufacturing. As you see on the screen, on your screen, on presented paper, first speaker will be our colleague Petr Henyš. He is his domain is computational biomechanics, mechanics, and metamaterials. He works at Technical University of Liberec, and the second speaker is me, and my interest is quite bright. I'm mechatronic, and I'm focused on application of 3D printing technologies. Today's speech is focused to robotic hands, but another interest is focused to 3D printing systems in construction. So it will be the next seminar next week about this topic. But let me invite the first speaker, Associate Professor Petr Henyš, and he will present his topic, mechanical metamaterials. I don't know how long, but it will be approximately a couple of minutes, let's say 45, I don't know. Well, it's your turn, Petr. You can speak.
Okay, so hello everyone. So thank you, Honza, for my introduction. I am a computational engineer dealing with the biomechanics, mechanics, and also with passionating in metamaterials, right? And so I will now try to share my screen. So please be patient. I will try it. Okay. So I hope you see my presentation, at least the first slide. Okay, so as already was said, that I'm dealing with the metamaterials and also with the mechanical engineering, and today I'd like to speak about the a brand of materials called like metamaterials, and more precisely, I will talk about the computational aspects of how to handle the design of metamaterials, and also what is a necessary computational approach required for the designing of mechanical metamaterials, right? Okay. So firstly, very briefly, the first part will be an introduction. I will try to explain what is meant by a metamaterial, and then I will move to handling a metamaterial design from a computational perspective, which will be more focused on implementing some specific computational approach to properly handle a most often used design, which is periodicity. And then I will show some results, including a benchmark, so some discrete methods, and then we can discuss and conclude what can be, or how it can be used, that what is the connectivity with the soft robotics, and also to be more concrete to using in in a hand prosthesis, and so one which is actually a domain of Hansa. Okay, so when we try to type term metamaterials in Google, Google will give you back quite broad number of images, right? As you can see here, there is a lot of things written around the metamaterials. It's a topic, very trendy topic. Use it across all broad band of the scientific disciplines, right? From, let's say, the acoustic to quantum physics, even in quantum physics, or for, let's say, more engineering approaches. So the metamaterial is something which is a very trend topic. And the reason, at least in my opinion, is the following. A very usual way how to work with the materials and how to use material in our problem to solve our engineering or material problem is to define a problem first, and then to try to find a material in nature, right? And we usually use we can call it as a combinatorial design. This is, by the way, not the same design as I will introduce later, but I want to say that having a problem, we usually solve it in that way. We try to find a material in nature, and we try to combine different approaches and materials, right? And then what we actually do, we just pick up the best one, which is what's suitable for our problem, right? And the metamaterial term actually give us another way to solve our problem, right? We still have to first say what is our problem, right? For example, I would say very quickly, we have an airplane, and what we know, we need a very strong and fatigue-resistant material while being pretty light, right? Which is quite difficult to fill, right? And now you would ask to, okay, I have this criteria which are quite strong, and it's not easy to find a good material, I mean, at least in the nature, right? And then I will come with the metamaterial paradigm. I would call it more as a paradigm because it's actually it is actually a paradigm, and it says that if I have my problem defined, I would precisely architect the material, right? So I will start, let's say, from bottom to top. So firstly, I will design the microarchitecture, so microstructure. Let's say I can start with the very small scale, including micrometers, maybe nanometers in the future, and then I can quite easily extrapolate it to our micro world and produce design the structure what I need to for my problem. One of the most influential factor for using and mass using metamaterials is having a technology how to produce that, right? Because as we will see later, the metamaterial is nothing less the sophisticated structure which has its material properties or physical properties controlled by the geometrical and topological properties. So we can very simply imagine it as a lattice, and this lattice has some geometrical and topological properties. And now the question is how to produce that, right? Conventional technologies are not well suited for such a structure. So here comes on the light the 3D printing. So the 3D printing is very important for for using a metamaterials, because it is the currently only the way how to produce a metamaterial. Okay, so then I try to say to explain what is metamaterial. And the good thing on the metamaterial is that I can not only design let's say standard properties, for example standard mechanical properties as we know, but I can also try to design some uncommon properties. For example, where you know metamaterials are so-called exotic materials, which says nothing less than it has a partial ratio which is a negative, right? So it's true that some of the crystals in nature are also able are also capable to have a negative Poisson ratio, but in engineering structures, or engineering materials, it's very uncommon. And with the metamaterials, we can design very simply the exotic structure, which has a Poisson ratio, what we exactly need. And also there are another properties which we can switch from positive to negative, right? Like I would say we could also have a negative stiffness, we can have a negative mass transport, and so on, so on. So there are a lot of things we can find which are not really common in nature, but with the metamaterials we can really design that, right? So in briefly, the metamaterial is a way how to design a new material which has a property what we precisely need for our purpose. So that's the good thing, and the bad thing is actually how to design that, right? So now we just I just mentioned that we mostly control the metamaterial properties by geometrical and topological properties, right? And it's mean that we just design a lattice, and this lattice has some some properties, and now we should define how to design, right? How to connect the lattice, so let's say lattice properties with the resulting mechanical or more broadly physical properties. That's something which is the most difficult part in metamaterials, and it is likely largely unexplored in the scientific community. And of course, this is a very hot topic, which is now really quickly progressing. And we may split up the design of metamaterials in two main parts, right? The first part is to really how to explore the space design, what we can use for our purpose. For example, me and my student will more deeply study we call it as a combinatorial design, right? Which is in our opinion quite promising a way how to shape the geometrical structure to do precisely what we need, right? It was already documented by the colleagues, and but it's we believe there is still pretty open door to improve a lot of things and use that study as a pilot study for our purpose. The good thing on combinatorial design is that it uncovers really large area of design space of quite simple geometrical and topological units, right? Actually, it works as a Lego. So you will just create a very simple structural units which has some properties, and then with the clever combination of those structures, you can reach properties so you required, right? This design will be, of course, used for soft robotics because it can be quite well extended to active structure parts. So we can also not design the metamaterial, which is let's call it passive, but can be also very active with the simple structural units, which actually provide the active movement, either a rotational or translational, no matter. And well, this is only one of the way how to drive our soft robotics models to reshape how we need. The second thing is, and what I will talk today mostly is, okay, well, we design a metamaterial, and then we need to somehow evaluate the metamaterial properties, right? And as I already said, that the metamaterial is mostly composed from some small structure units, right? As the lattice is, right? You know that the lattice is actually, if it's periodic one, then it is composed from many small parts. And this is a challenge for known computational methods, which are usually used to evaluate the material performance, because we need to couple actually at least two scales. The first one is the scale of let's call it as a macro scale of our model. So it's actually our object of interest. Let's say for example the prosthesis, the hand, right? But this hand is composed from many small parts, and those parts has some important properties which are used to extrapolate those properties to our whole model. And that's the big issue, because we need to, in our computational model, include both features from both scales, right? So you need to know precisely the shape of our model, and also simultaneously we had to know what happens inside, right, in our structural units, to precisely know and evaluate what our material does. So it's but this is an issue which is not uncommon in nature, where usually we could start from the electronic structure ab initio, which is the base of everything, right? Going through the atomistics, then we can switch to microstructures, and then at the end we have a microscales, right? I will not take into account the cosmology, but let's call it at a scale of our being. So in our case, we will skip the electronics and atomistics, although it is possible as well, and we'll just focus on a coupling of microstructure and the microstructure of our lattice, or if you want, the metamaterial, with the microscale, which is meant by a product we compose of, right? So for that part, we need to somehow couple those two scales to precisely evaluate, as I said, the physical properties of our design and metamaterials, if it does what we really wanted to do. And for that, we could use another approach, which is called as a multi-scale approach. And this approach is it's a more broad approach, which is which actually tells you that you will see your model in multiple scales, either temporal or spatial one. But in our case, we will use it exclusively as a computational approach, which means that we will have a computer model of metamaterial, and we'll try to simulate and evaluate its properties at least 2 scales. That's why we call it a multi-scale, right? But this it is generally a quite difficult task, and even more difficult in computational domain. So mostly we will use the multi-scale approach to evaluate and design a microstructure of metamaterials, because we can also use that, right? For example, if we design the lattice structure, we can immediately infer for example, the elastic properties of the lattice unit, right? Sorry, of the lattice unit structure, and to see what it exactly does, and what mechanical properties it has, right? So that's actually very good, because now we can extrapolate the elastic properties from very small scale of the smallest lattice feature to the micro scale, for example, to all model we have. Another good thing on the multi-scale approach is that we can also couple not just physics as the same physics on both scales, but you can also couple different physics, which is far more difficult, but it is also possible, right? For example, we can couple electromechanics, we can couple, of course, thermomechanics, or another things. Electromechanics is electrochemomechanics is also very interesting, because there is a growing family of electroactive polymers, and those polymers can be controlled by another physical fields, for example, the electric fields. And for that, it is really promising to use multi-scale approaches to be able to, with of course with the different physics on both scales, to be able to evaluate not only the let's say the mechanical properties, but also the mechanical properties controlled by the external fields, like electricity. Of course, one could say, I can use, I will buy a computer which is very strong, or I will pay my Azure or another cloud services, and will ask to use finite elements to just compute the mechanical response of my whole lattice, right? Of course, that could be to some extent possible, but the extent is really small, actually, right? Even with the modern computers, with the huge power, and also with the huge memory resources, we are not able to solve both features, the features at the small scale and the bigger scale together simultaneously, which is very obvious if one scale is in micrometers and the second scale is in meters, right? That's the amplitudes. It's so different, so we are not able to solve it efficiently without using more sophisticated methods, like a multi-scale approach, for example. So if I talk about the multi-scale concept, I should say what is the idea, right? So there is a figure which is one of the fundamental part of the multi-scale approach, and it is called as homogenization. let's consider the most left figure, which is our metamaterial, or you can imagine it as a composite, doesn't matter. And the most important part is that it has a microscale and also features in microscale, right? So you can see some circular parts which represents our microscale features, which produce mechanical or physical properties we need. So also we have some boundary conditions. If you will talk about the computational model, so those boundary conditions are very usual, right? So you need to somehow fix the model, not being floating in the space, and also we need to somehow load the model to know the response on how our model reacts to the loading, right? Which is called as the in our case omega Newman boundary conditions. So let's have this object, and then we would like to ask how to if I love this model, what happens inside our structure? I mean, what happens on the level of the circular structure, the feature which lives in microscale, right? I cannot do it simply with the finite elements. So I have to use an approach. There's another approach, but the homogenization is one of the most, let's say, powerful and also flexible approach. So what we will do, we will replace our model with another model which has properties, I mean the macro properties, the same as our micro model. What that means? If you would load the most left figure, the model on the most left figure, you will get a response, right? If you are blind, you will just obtain, and you will not see the inside the model, so you don't know actually what is inside, but you will get a response, which is, I don't know, we can talk about stress strain curve, for example, right? You will see some response, and the truth is that if we don't know what kind of microstructure we have, we just consider our model as a black box, right? We just have some micro response, a global response, and nothing more. What that means from for our multiscale concept is that we can also think that this macro response was obtained with the material which has no microstructure, but it has just a kind of the material which actually gives the same macro response as our microstructure, right? That's why the middle object is not containing the micro features, and this is like a continuous material. So that's the idea of homogenization. We will replace the microstructure with something which is a continuous material, but it is the same global response. So basically, we don't know what if we use a microstructure or we use a continuous material, unless we know we have some additional information on the microstructure of our model. Well, now the question is how we get such continuous material properties, right? How we get it? We can usually call it as an effective properties, right? Because we just replace our original microstructure with something which is completely different, but it has just the same response, a global response, right? And now the question is how we can get it. Okay, there is a way how to get it. So we just under some circumstances we kept a small piece of our microstructure, something we call it as a representative model or representative volume or area, depending on the dimension we use, and say, okay, this is a representative and enough small structure which can be used to define such effective physical properties. So we call it, this is the figure, most right figure, where we call it as a representative volume element, which contains a microstructure we want to design, right? So at the end, if we design a metamaterial or even composite, doesn't matter, then we usually start working firstly with the representative volume element, right? In terms of metamaterials, it means that you will just draw the unit cell if the metamaterial is periodic, and then to load this unit cell and ask for elastic properties. And if we get it right, then we can extrapolate it by the homogenization approach to the rest of our macro model. Well, so this is well explored area in coupling or computational coupling of two or even more scales, right? To properly formulate the representative volume element, we usually need also to define precisely boundary conditions, right? And this is actually very tricky because the boundary conditions should somehow reflect the microstructure and how the microstructure is placed in our macro model. The basic differences are between the materials or metamaterials which are periodic, and also the materials which are not periodic, we call it aperiodic, right? Both approaches are has some constants and also some drawbacks. But anyway, we still need to know precisely how to define the boundary conditions, which should reflect the periodicity or aperiodicity of our metamaterial. What is really interesting is that if we use for both cases periodic boundary conditions, it gives us very satisfying results, which is really interesting because one could not or may not have expected that the periodic boundary conditions are not also suitable for a structure which is not periodic, right? But actually it works quite well. And the reason is following. When we use a periodic structure, periodic boundary conditions on a model which is representative enough, I mean, if it takes enough information about our microstructure, then we can really use periodic boundary conditions, right, without destroying the information in the at the micro model, right? And this is also this example. What you see here is there is a quite scene that you can see that the microstructures, the small spheres are really are not periodic, right? This is quite randomly placed spheres, and if there is if the RV model is bigger enough, so it can contain most of the useful information for us, then we can still use the periodic boundary conditions. That's pretty good, pretty cool. We will continue with the periodic boundary conditions. Okay, so well, we want to define a periodic boundary conditions for our model, and Once we will have it, then we can somehow load our RVE, right, to give this deformation. We call it as a unitary deformation, right? And those unitary deformation actually are actually given by degrees of freedom in our model, right? So if we have a 3D model, we have 6 degrees of freedom. So we have to use some 6 independent loadings, which produce 6 another set of independent responses, which are then used for our to somehow infer our elastic properties. Well, if we have this response, then we use something like a homogenization operator. And this is the part why we call it this approach as a homogenization, because now what we will do, we will just take the response of our whole ROE and we will shrink it to one scalar number, right? So we'll, for example, this example is about the elastic properties, right? So what we'll do, we just apply a unitary loads and 6 degrees of freedom. We'll get adequate response in terms of the stresses, right? And we will not get the one number. We will get a stress tensor, which has for Cauchy continuum 6 independent components, and those components, if we use, for example, finite element, are not constant over the whole RVE, right? So what should we do next? We should we pick up the one of some of the value, or what? Actually, we will not pick up any value. We will just integrate the stress tensor over the whole RV domain and get one stress tensor, which is called as an effective, right? And if we apply this approach, then we will get the effective properties what we were talking before. So before using a multi-scale approach in metamaterials, we need to ask for some assumptions, right? The first assumption is that the first order homogenization we used is actually scale independent, which means that we can model efficiently only scales. Let's focus on 2 scales which are really far from each other. It means that the macroscale is much bigger than microscale, right? And also we should somehow fulfill that the features in the microscale should be also smaller than the scale of the representative volume element. If we are somehow able to fill those conditions, actually the true way is that we don't have to fulfill that, right? It will still work, but it will not give us the right results, because once the scales are approaching together, it means that one scale can influence the second one, and it means that which is not taken account in the first order homogenization. In other words, it doesn't use it's not able to scale to distinguish between the scales, right? It is because we, as you've seen, the RVE is actually can be really bigger for us, right? But still, it's not influenced by the macro model. So once we will trust our scale separation, we should use proper boundary conditions, right? So we can use basically 3 types of boundary conditions very usual boundary conditions, which are Dirichlet one, Neumann, and also the periodic, which are most interesting for the multi-scale coupling and homogenization. Once you also set the boundary conditions, you also need to be able to compute the volume area integral of the quantities of the interest. For example, if you want to know the elastic tensor, we can just take our stress tensor, do some temporal special averaging, and with that integral, and then we can get us call it as an effective stress tensor, right? So this is working, but there is one thing which also needs to be fulfilled, and this is we call it as an energy equivalence between the scales. It means that we cannot usually with the first order homogenization allow that the energy is dissipating over the scales, right? So if we want to use a first order homogenization, you should always expected that the energy is constant across the scales. It means that if I have some energy at the micromodel, it should be reflected at the energy at my macromodel, right? It cannot be lost or cannot be added, of course, right? And finally, this is already more precise and more focused on mechanical metamaterials, right? What do we if we design a mechanical metamaterials or evaluated its mechanical properties, we are always interested in elastic properties, right? Very often it's most interesting quantity. For example, knowing the anisotropy, knowing the what are the direction of the most stiffer directions, what is the for example the partial ratio, and so on. And for that, we need to compute the elastic tensor, which is in virtue of multi-scale modeling and homogenization, it is actually a tangent of our RVE model, which is defined, of course, as for example, this is actually using it actually uses the Huxlaf, right, which is defined as a partial diffraction of the stress tensor and the effective one with respect to the strain applied, which is the unitary loading at those direction we need. Well, so if we want to apply our periodic boundary conditions, as I said, the periodic boundary conditions are really effective even for non-periodic metamaterials as well and of course very good for periodic metamaterials. And some can take it as a compromise between the Neumann boundary conditions and the Dirichlet boundary conditions. And the reason is following. If you apply the Neumann boundary conditions, your system for displacement-driven finite elements model is always underestimating the resultant elastic properties, while the Dirichlet boundary conditions overestimating the stiffness, which means that we can see it as a lower and upper bound of our stiffness properties of our computational model. And what is interesting is that the periodic conditions are the most well reflecting conditions for having most realistic and less biased the elastic properties, right? But applying periodic boundary conditions requires the conformal mesh. What that means is that if, for example, you see the most left figure, there is a simple 2D model, geometry of, let's say, one. It can be also in concept as a metamaterial, but without any specific properties. But you can see that the green stars marking the nodes, the finite element nodes, are conformal on both sides, right? Well, I call it as a negative and positive. It is in some just assumptions and use the terms how to define what is positive and negative in terms of the periodic boundary conditions. We can still define it even on the 3D, right? Where you see that still, if the geometry is simple, then we can still force the software, the algorithm for meshing, the discretizing the domain to create the mesh which is conformal at its boundaries, right? Either at the faces or at the edges. But if the geometry is more complex, it doesn't matter if it's the metamaterial or another volume. So then it's much more difficult to somehow fulfill the periodicity, and actually much better is to somehow work with the mesh which is not conformal. However, if you want to use a non-conformal mesh for achieving periodicity, you have to somehow modify the finite element model, and that's something which is pretty tricky and needs some parts to be added and to be controlled. Otherwise, you will not get satisfying results, of course. You can do it. For example, commercial softwares use that in, of course, use some approaches which, however, are not very much effective. And the reason is following: because if you want to couple two scales, right? What you are usually interested in macro scale is to know at each point of interest how the RV model is loaded and what is the response, right? So it means that each point of interest in macro model, I have to solve small finite element model composing of my RVE, which needs to be periodic. So your RVE finite element model should be really, really effective, because otherwise you will have really, really long time computation, right? So using an effective formulation of periodic boundary conditions is a paramount in using to the coupling of the macro scale and say micro scale in design of metamaterials. So for that, you have to we try to formulate the micro scale finite element model to be more effective and to try to find the new way how to define the periodic boundary conditions even on the mesh which is not conformal at its boundaries. Well, start with some simple math, right? This is just an exemplary of some very simple linear elastostatic model, which is where the equations of Cauchy continuum and the boundary conditions are defined on the very simple 2D model, a planar model. And what is more interesting is the definition of the boundary conditions controlling the periodicity. What do you say by periodicity? You actually requires that in terms of the canonical metamaterials, you will use quantities defining our energy and also defining the displacement and also the stress, right? And if our model should be periodic, we want to have our displacement to be periodic as well. So we need to somehow force the periodicity of displacement on opposite sides of our model, which means in according to this figure that we need to know that the displacement living on the edges on the edge 1, 4, definite from points 1, 4 and 2, 3 to be the same, and this should also be required on the edges defined point 1 and 2 and 4 and 3, right? And of course, what happens with the stress? But by definition of the stress, which is nothing less than a gradient of the deformation, of the displacement. So if the displacement is periodic, the stress should be periodic, so anti-periodic, right? So we have several options how to force our model to consider the displacement field being periodic. We can use a method called like a meshless method, which stands on the interpolation of the displacement field on the boundaries, which is quite robust, but it has some drawbacks. Or you can work with methods which using finite elements discretization, which the most known method is we call as a mode method, which is very well known in contact mechanics. And there is another method we try to apply is we call it as a niches method. And this method, like the Marta method, it tries to handle the constraints, the periodicity constraints in our computational model. We call it as a weakly, right? It means just not using a method. Weakly means that you try to satisfy those conditions in average, right? Not precisely, luckily, but just in average. I think this is some interesting consequences. Just to briefly show what's going in meshless treatment. So this is it is kind of the interpolation. You will just take your displacement field on the boundaries, and you will try to replace it by an interpolator with some well-defined basis function, right? And what you will do, you will get the same with the same interpolation method you already obtained on one side. You will use it for the opposite side, right? And once you will do it, then you will actually get the same. Displacement field on both sides, no matter if the nodes you use it are conformal or not, right? More technically, it just means that you will get you will take the original computational the form of the energy and replace it by transforming to another degrees of freedom, which is nothing more than a set of degrees of freedom previous, enriched by degrees of freedom given by interpolator. This method is quite robust, but the bad thing is that it somehow decrease the sparsity in the resultant matrices used for solving algebraically our problem in finite elements, right? So it has some drawbacks, mainly concerning with that. Also, the truth is that also it depends on the order of the interpolation. So for example, if the displacement is a complex shape or complex evolving, then for example, you need to manually or at least visually somehow adjust the order of the interpolation shape. Otherwise, you will not get the precise results, and the model will then behaves as more stiff. Well, just briefly to a mortar method, I will before define two very useful operators. What I mean by operators, I will not just every time write u plus minus u negative, right? So I will just put it in one symbol, and we call it this symbol as a jump, right? because it is basically a definition of the jump in the field, right? If the U positive and U negative is not the same, then you will get the jump. What you want to know, what you want to do, you want to minimize the results, the difference between one U plus and a U minus, right? And there is another operator, also very useful, and this actually is, we call it as an average operator, which or even a weighted average operator, which says nothing less than the what is the relation of the stress on both sides. So once we define those two operators, so we can define also the energy or the elastic energy of our representative volume element of our metamaterial unit, right? We can define many ways. For example, I choose the this kind of the weak form of the Cauchy partial differential equations, but this partial differential equation is enriched by Lagrange multipliers, and you know the Lagrange multipliers. It is another variable which is very often used in optimizations, for example, to enrich some very general constraints in a strong form. And here the Lagrange multipliers are lambda multipliers. Also, these Lagrange multipliers should live in some suitable interpolation or finite element space, right? So what we have to do, of course, in solving our problem is that the first term from left is a bulk energy, and the second and third term are the terms for multipliers. There are two because of the symmetry, and the right hand side is nothing more than the loading term, right? So once you will solve that. And then this equation we can solve, for example, by finite elements, right? And we'll get a set of algebraic equations written in a metric form, and then we can very simply solve that problem. Well, what is not good on the Lagrange multipliers is that how to choose precisely the space of, well, we want to live those Lagrange multipliers. So that's not really easy to precisely know. And so we have to try it and so on, and to see the stability of our problem. And also the Lagrange multipliers given produces a system of equations which are actually not so easy to solve, because now we have we call it as a saddle point problem, because there are some parts in our equations which where the on the diagonals where we have a zero. So it's not so easy to then it actually the most practical it means it restricts somehow using a variety of the algebraic solvers or the metric solvers to get our problem solved. So we tried another way. And by the way, I also forget to tell that if we have a Lagrange multipliers, it also increases the degrees of freedom. So the model is bigger and bigger once we try to refine the faces or edges containing those Lagrange multipliers. So there is a way we found a way how to partially solve such disadvantages of Lagrange multipliers and a meshless method. We actually basically take those multipliers and replace it by a flux, which is this term, right? But if we will just simply replace it by a flux, we will get a system which is not solvable. In math, it means that it's not cohesive and it's not stable anymore. So we need to add also we call it as a stability terms, or which help us to solve our problem. The good thing on this is now we define it flux as variables which are already in our system, so it doesn't inflate the system of the equation. So solvability is the same. We also found that the constraints are now handled weakly, which actually which forces us to somehow also define what we call it as a stabilization parameter. But this stabilization parameter for our method can be quite well estimated as at least in lower bounds, right? Which is pretty good, because now you have we call it as a penalty term, right? And if you know that the penalty term is a penalty is always a nightmare in numerics, because you have to somehow, well, you know, empirically somehow infer. It means practically you have to choose which range of values you can use for a problem. But in our case, we can precisely estimate what should the penalty be, right? That's very different. So we define the new weak form containing not just only the bulk form, which is the first term from left, but also the rest. There is now more terms defined on the boundary, but those terms it's really easy to solve or easy to produce with the finite elements than using Lagrange multipliers or meshless method. Okay, there is some technicalities concerning the finite elements. If you don't mind, I will skip it. And now I will just briefly describe how to integrate quantities of interest on non-Manchik interface in 2D and also in 3D. Well, if you have two non-conforming meshes, right, and you want to which together produces an interface, either 2D or 3D, right, of course immersed, then you also you want to somehow work with the weak PDEs, then it means for you that you have to be able to integrate on these interfaces, right? And this is also not so really easy, and it's very known. It's a nightmare in contact mechanics, right? And here we propose a method which using something called as an intermediated surface or edge in 2D, which is used to integrate those values. What it means, if you integrate in your PDE or weak PDE, you need to integrate numerically, right? You don't have any choice. That's why you do finite element discretization. And you need to integrate in Gaussian points very usually. But now you have actually a surface or two surfaces which are not conformal, so your Gaussian point also not conforming, right? So you need to know what is the Gaussian point for on one side, what is the correspondence on the second side, right? So there is a variety of methods, mostly concerning from the computational geometry. So in our cases, we define something like an intermediate surface or edge, and then what we did, we just integrate on this surface, and then or we created the Gaussian point on this surface, and then what we did, we remap those Gaussian points on both sides and get an integration of our quantities. You may ask, why so difficult? That's very simple, because if we take a slide back, you see that the operators I defined are actually composed from quantities from both sides, right? And so you have one integral operator, and inside you have two quantities which lives in different domain, right? So how you can do it? Right? You cannot simply just integrate on one domain, and which is then correct for one quantity, but not definitely correct on the second quantity unless it is identity, right? Of course. So you need to find some mapping scheme, which we tried in our cases, that we define firstly as something like an intermediate surface, integration surface, and then we try to remap those Gaussian points to both sides. So if we did in that way, we get really really precise results. Actually, we get exact results in terms of the order of the integration, in terms of the order of the quantities integrated, and also the interpolators usage, right? So which is actually we usually need to get for our which we usually need if we trying to find a new integration schema, for example. Well, in 2D, it's quite easy. You can use many tricks from computational geometry, but in 3D, it's much more challenging, because now you don't work with just a simple edge, which you can simply segment, right? You can make more segments from that, but now you have some intermediate surface, and you get then a surface, and this surface contains an object, which is basically a projection of one element from one side to second element, and the element from the other side. And then you need to know you need to find the intersection, right? But still, it's not enough, because if you have an intersection of two, let's say, triangles as here, you will get an object which is not a triangle anymore, it's a polygon. And but how to find out the Gaussian or and suitable integration scheme of a polygon? Well, the simplest way is to discretize this polygon itself into triangles, which is quite easy. We will get just a center of polygon, and then just draw a straight lines for each vertex of such polygon, and we'll get the quite precise integration of this. So this is the additional step you have to do it in a 3D, and then you can use the well-formulated Gaussian integration on a triangles to get the exact integrals in your weak form of PD, right? The only this is the only one differences in 3D. It is more challenging from the computational geometry, because you have many choices what could happen, right? There are many situations. What happens with how the triangles can be intersected, right? Can be fully intersected, partially intersected, and for each case you have to write a new case where you have to be very careful what what you should do, right? So from that point of view, it's more complicated, but this is quite well doable. So once you will have it, then you can use the same way as for 2D and get the precise integration of your quantities of your energy, actually, right? Well, so let me briefly just explain some tests, some benchmarks models, which we used recently. Firstly, it's not concerning precisely the metamaterials. I use it in another study. If we would have a time, I could also introduce that. But the first model is kind of the composite. The second model is a coupling of two scales, right? By the way, those the methods introduced, so the meshless one, the mortar method, and the niche one. Regarding the meshless, we use a Lagrange polynomial for interpolation of the order 3 to 6, right? And in some cases, we also use, instead of Lagrange polynomial, the splines, right? The splines are much more flexible, but the truth is that they are a bit more computationally difficult, more computationally intensive. Well, in case of mortar method, we needed to find suitable finite elements where, well, actually the interpolation elements of multipliers and the displacement field, and we found that the compatible spaces is Lagrange polynomials of the first order for both quantities of interest, and we use a Gaussian radio integration scheme for 2D as well for 3D, or in one case was 3 integration points, and 3D it was 5 integration points. In each method, there is actually only one parameter to choose, is the alpha, which tells you if your form is symmetric or not. So for alpha 0.5, we got a symmetric form. This means that the matrices, underlying matrices are symmetric, so you can use very large variety of solvers, very effective solvers, for example. Right? And the last thing is, I didn't mention it all the presentation, is that if we would try even in commercial softwares applied periodic boundary conditions, and what would happen is that your model would not work properly, and you will find that your model is actually translating, right? Because the periodic boundary conditions or periodicity is not sufficient condition for being the model precisely defined, right? Because the periodicity just removes the rotation, right? So your 2D model will not rotate anymore, but still can translate into any direction, right? So if you want to really have a solvable periodic model without any Dirichlet conditions or Neumann conditions, you need to do something more than this. So there is some another way, right? What it means that you want to, if you imagine that you have a 2D model, I'll just focus on 2D model, and 3D model is analogous, but 2D model, it means applying only periodic boundary conditions will remove the rotation, so your body will not rotate anymore, but still can move from right to left, top, bottom, doesn't matter. But what that means, right, from the solution point of view, it actually means that you have to somehow, if you solve the problem, you have to somehow remove the mean value, right? And you know why? Because if you imagine that, right, if you have a let's say a displacement formulated on in your model, you deform it somehow, right? And then you take this model deformed and move it, I don't know, 5 meters away, then the deformation will be the same, right? You will just move it a bit far from its original position. What that means is that if you would get this, if you would get an average value from the displacement field from original position and the new position, then you will get some non-zero value, which is exactly the translation from one point to another point, right? And from that idea, you can also somehow the mean value remove from your model by simply adding an additional term in your weak PDE. For example, you can say, okay, so let's constrain that the mean value should be 0, right? Which tells you that the position, the translation is not allowed anymore. And you can also add the addition. This actually means that you will add the additional term, which is quite similar to periodicity, but it just tells you that it is just an integral over the whole domain of the displacement field, right? And you will just say, okay, this I want to be 0, right? So you will just and then you can force it by the penalty, or you can force it even by a Nietzsche or mortar, doesn't matter what you choose. In our cases, we found that the most efficient was to choose a penalty to force the mean value of displacement film being 0. So we control it by another time, but by another time penalty B1. What was interesting was it was almost insensitive to value, so it was pretty good for us. It was just influencing somehow the condition number, but it was not so significant with respect to the way how to solve the problem. So we use that one. So once you use that the modeling homogenization approach, let's say we choose RV, which is a composite, right? It's just some spherical parts, and you want to know what are the elastic properties, right? Or even what are the, for example, what is the stress tensor, the effective stress tensor, and you will find it that both method works quite well, except that the nature method is much more faster. It's the same in 3D, right? This is already not this is the elastic property, so you can see it's quite symmetric, right? Even it's not of course, even it's not periodic. It's actually a random realization of from some simple Gaussian field, but still it does you can still get the results which or the elastic properties which can be even isotropic, right? Of course, but of course it can be also orthotropic, which is for example the most cases for aesthetic or mechanical materials. Well, if you want to couple to scales, for example, a very simple example of beam, or which is composed from very simple unit, which can be considered also as metamaterials with the hard inclusion. Then you can build up a scheme which is nothing more than you will provide a communication between the macro finite element model and micro finite element model, right? And you will just provide a communication of terms that you will, once you apply the deformation in the macro model, you will put it inside the micro model, and from the micro model you will get the elastic constant as well as the stress field, and this will go to macro model, and you will get you will for nonlinear elastic properties, right? If the micro model is nonlinear, you should use some iterative scheme to get the equilibrium in a macro model. If it's an elastic properties, then you can just compute the micro model once, right? And the elastic properties and the stress will be every time the same for every loading, because it's independent on the loading path, because it's a linear one. And there is just a few illustration, right, for 3 methods. So what you see is just a very simple cantilever, which is beam, or which is bent. And you will ask, okay, I see the macro response, right? I see where is my stress, where is my deformation. That's obvious, but that was not the reason why I computed the decoupled to scales, right? I want to precisely know what happens at my micro scale, right? Okay, I see, because I actually couple those 2 scales. So now I see what happens around my inclusion in a scales which is much more less than the scale of the beam itself, right? This is the reason why we use that method, right? So now you can see not just only the macro scale, but you see also what happens inside your metamaterials or composite domain. Well, if I would somehow compare those methods, it's that I would say that of course, our methods shares some parts of state-of-the-art methods in literature, mainly the multi method and meshless one, and actually remove some most of the disadvantages of those methods, right? So the with respect the polynomial interpolation from the meshless method, it doesn't modify the sparsity. The sparsity is well preserved. So using a standard solvers of linear system is very efficient. With respect the mortar method, it doesn't inflate the matrices, the system of equations, because it doesn't contain any any Lagrange multipliers. And with respect to penalty method, which could be also used, it has an advantage is that we can, for certain kind of finite elements, we can find a lower bound of the penalty term used in Nietzsche's method. So everything is actually automatized. You don't have to care about how to tune or how to set up your model. It will do it. It will because it doesn't require any manual setup. Unlike the meshless method or the mortar method, where even you have to time to times, if you have a new problem, you have to found how you will, what kind of finite elements you will use for mortar method, for Lagrange multipliers. It is not obvious, because you need to from mathematics you have to fulfill, we call it as an inf sub stability conditions or Babushka-Basic conditions to be sure that your model, that your system is cohesive and solvable. And of course, instead of simple positive definite system of equations, you will get a system which is called a saddle point problem, because there are some zeros on diagonals. So you cannot simply use rhetoric solvers and so on, because, for example, LU, because there is some problem with pivoting, which is of course problematic. But of course, always there is many improvements you can do. Now we demonstrate our solution on linear static problem, which is of course very often used and very sufficient. But of course, more multi-physical problems could be solved too. For example, as I said at the beginning of the presentation, using, for example, the coupling of different physics and different scales will be much more interesting. And our estimation of lower bound in Nietzsche's method is now, I would say it's half and half. I mean, it's a half of mathematically rigorous, and the second one is an empirical. It's estimated empirically, which is of course, and this is just of lack of efficient and analyzing the some mathematical properties of the Nietzsche form we defined. And of course, very often you find that filling the criterion of a scale separation is not possible. This is not simply it's not simply possible, and what means that the one scale is affecting the another scale. In that case, we can somehow use not just simply linear homogenization we use here, but you can use a high order homogenization, which allows us to also include the scale and scale size effects in our micro and macro model. And the last thing is what happens if you try to couple? For example, this is very closely related to metamaterials, right? Very often the metamaterials are formulated as a lattice, and this lattice has rather struts than a solids, and so it's much more efficient to model the lattice structure as a beams, for example, right? And the beams usually has more than 3 degrees of freedom to solve, but also have a rotation degrees of freedom, and that's much more complicated for our homogenization approach, because once you have a rotation degrees of freedom, you have to somehow include it in your continuum theory. And because the standard Cauchy continuum, it works just only with the translation degrees of freedom. But if you have also rotation degrees of freedom, then it's much more difficult, and you have to switch to more sophisticated, like a Casurat or some other more generalized continuum theories. But this is also doable. It's just a question of implementation, of course. So at the end, thank you for your attention.